Hi guys, I'm Katie Hannon, and today we're going to explore, we're going to look at patterns. Hi guys, I'm Katie Hannon, and today we're going to look at patterns in algebra, and we're going to take a look at a simple stick pattern, and we're going to kind of come up with an algebraic rule, but really understand where the rule comes from. So the questions that we're going to answer today are how many sticks are in the next diagram, how many sticks are in the 20th diagram, and write an algebraic rule to describe the system. And the system that we're talking about is this table up here. It's saying step and number of sticks. And for one step, there's 4 sticks. For 2 steps, there's 7 sticks. And for 3 steps, there's 10 sticks. And the picture is shown below. It's basically saying the same thing. For 1, there's 4. For the second, there's 7. For the third, there's 10. So I kind of rewrote that table to this. On the left side of the table, I wrote number of squares, and that's 1, 2, 3. And on the right side, I wrote number of sticks, and that's 4, 7, 10. The reason why I wrote number of squares and not steps is because it makes more sense to compare the number of squares to the matches. Because because the sticks make up the square. So for this one square, there's 4 matches to make it up. For these 2 squares, there's 7 matches to make it up. So that's why I use squares instead of sticks, and they're matchsticks. So that's why I'll call them matches or sticks. So 1 for 4, 2 for 7, 3 for 10. So this table basically describes numerically what's going on in the pattern instead of just giving you the blocks itself. So to find out how many is the next one, you might notice that in the right-hand column, it goes 4, 7, 10. So if you notice, you're basically adding 3 to each one. So 4 plus 3 is 7, 7 plus 3 is 10. So you could add 3, and you could keep going, add 3 to find the term that you need. But the problem with that is that you need to know what the 4th term is, what the 5th term is, what the 6th term is, and so on in the 9th term to add 3 to find the 10th term, or you need to know what the 19th term is to find the 20th term. And so this type of rule is recursion, where we need to know the one before it, before we can find the one that we actually need to find. The benefit of that is that we have to come up with a rule for it, and once we come up with the rule, we can jump to whatever number we need to without having to know the terms before it. So in our question, it's saying 20th term. Well, if we find the algebraic rule, we don't have to solve all the numbers up to 20 to find out what 20 is. So that's good. But back to our table, I'm going to break up 4 and 7 to look a little different, and I'm going to erase it as I go, so keep up with me. So number of 6, I'm going to break it up because 4, we see that if you notice, in the pattern right here, you have 1 stick, and this is on purpose. You have 1 stick, and you're adding 3 sticks to it. So instead of having 4, we can rewrite it to say 1 plus 3. And in the second one, you already have your square, but you're adding 1 plus 3 plus 3. Because you're adding 2 things of 3. So instead of 7, you could do 1 plus 3 plus 3. Because like I said before, you keep adding 3 to each one. So for the third one, you're going to add 1 plus 3 plus 3 plus 3. So you can abbreviate the 3's by saying 1 group of 3 plus 1. Then 2 groups of 3 plus 1. Then 3 groups of 3 plus 1. So we can rewrite that. And we're going to do, 1 group of 3 plus 1. And there's 2 numbers of squares, so 2 groups of 3 plus 1. And then 3 is 3 groups of 3 plus 1. And when it's saying 1 group of 3, 2 groups of 3, 3 groups of 3, that's saying multiplication. So we can change it one more time And the reason why I'm taking you guys through it is so you understand the thinking process to understand the diagram that we've been given. So one group of three is basically saying 1 times 3 plus 1 because it's one group of three. And so we can rewrite that to 1 times 3 plus 1. And for the second group, it's saying 2 times 3 plus 1. And for the third one, it's saying, can you guess? 3 times 3 times 1. Or plus 1, excuse me. So now if you notice, the number of groups there are, is equal to the number of squares there are. So we see that there's 1 square and there's 1 group of 3. We see that there's 2 squares and there's 2 groups of 3. 3 squares, 3 groups of 3. And so on. And so we can make a rule out of this. So we can say that the number, we could say the number of sticks is equal to the number of squares. So like the number of sticks is equal to the number of squares times 3 plus 1. And so the number of sticks, which is also the number, so the number of sticks is equal to the number of squares times 3 plus 1. So now we can make an actual equation out of it, not actual algebraic rule for the thing, for the diagram. So if it's saying the number of sticks, we can make that n. And then it's saying is equal to the number of squares, so we can make it s for the squares, or sticks too. But we already put n for sticks, so that's why we're going to not use the same variable for it. So n equals s, so the number of sticks equals number of squares times 3 plus 1. So that's our algebraic rule for the whole thing. And so we went through this whole diagram and made our way through the whole thing. So let's go back to our questions and see if we can answer any of them. So how many sticks are in the next diagram, which is the fourth diagram? So now we can kind of just plug the number in to the rule that we just found. So if we're doing n, so that's our rule right here. And so if we're trying to find the fourth one, we just plug it in. So n equals 4 times 3 plus 1. So 4 times 3 is 12, plus 1, that's 13. So the fourth term is equal to 13. Now we need to know how many sticks are in the 20th diagram. Well, we can plug that in again. So n equals 20 times 3 plus 1. And that equals, so 20 times 3, that's 60. And 60 plus 1 is 61. So the 20th term would be 61. And this is where recursion comes back in because like I said before, once you find the rule, you can plug in any number that you need to. See, because we didn't need to find the 19th term and then add 3 to it. We could just automatically go to the 20th term by plugging in 20 to our algebraic rule that we just found, which is a lot easier and a lot faster to solve equations and find the nth term of the sequence. So our last question says, write an algebraic rule to describe the system. Well, we already did that. And remember, it's n equals s times 3 plus 1. So we looked at a diagram and we looked at patterns in algebra. We learned about recursion and we took a simple stick pattern and we came up with an algebraic rule based on the pattern.